Hey everyone, in this video we're going to go through some questions involving arithmetic sequences and geometric sequences. So just a quick recap of what arithmetic sequences are. So here we go. Remember there's a common difference. So if it's positive, it's going up, it's an increasing arithmetic sequence. If it's a negative common difference, then it's decreasing. Arithmetic sequences, if you were to graph them, would be linear. So if it was increasing, there it is, going up, decreasing, going down, but it's linear, right? It's going up or down by the same amount each time. Now, very important that you understand the recurrence relations for both arithmetic and geometric sequences. Remember, with a recurrence relation, there's things that stay the same. So the V0 equals always the same. Then you just got to work out what your initial value is. So you write V0 equals and then what the initial value is. And then we've got the relationship is Vn plus 1. You write that equals Vn. You write that. The only thing you need to work out is the D, all right, the common difference. So recurrence relations, you might have one where you're not using V. You might be using a different letter like A or B. That's okay. You just replace the letter. That's right. It doesn't always have to be V. But the V0 equals or the A0 equals or the B0 equals, always the same. And then you got the Vn plus 1 equals Vn, or it could be An plus 1 equals An, whatever it is. Just make sure, and I just remembered here, that you have these smaller, all right? They're not the same size. Like they're not normal font. They're, I think it's subscript, all right? It's down the bottom. It's hanging down the bottom. All right, and then your rule, the only things that change is your V0 and your D. All right, so if you can work out your initial value and a common difference, there should be no reason why you would get any of these questions wrong. All right, because you're just substituting in the initial value and your common difference. Now that's linear growth. If it was decay, the only difference is you've got a minus sign here now. All right, it's going down, it's not going up. So your common difference is now negative. All right, we're not going to, in this video, look at financial applications, all right, but just as a quick recap, arithmetic sequences, the financial applications are simple interest, loans and investments, flat rate depreciation, and unit cost depreciation. All right, let's have a quick look at geometric sequences. So remember, we go up by a common ratio. So we're multiplying each time. All right, we're never dividing, and I explained that in a previous video. We don't divide, we only multiply, because dividing is the same as multiplying by the reciprocal. So here you can see we're going down, or we're dividing by 2 each time. All right, but the common ratio, we do not divide, we multiply by the reciprocal. So instead of dividing by 2, we multiply by a half. All right, so just remember that. Oh, and one thing I didn't do in the previous video to work out what your common ratio is you just choose 2 consecutive numbers, and then it's just the second number divided by the first number. So for this one, it's 3. You can choose any 2 consecutive. 81 over 27 equals 3. Yeah, we could do 4 over 8 equals half, which is the same as 0.5. All right, so that's how you work out the common ratio. Probably we'll do that when we look at some videos. Remembering the graphs are not linear this time. All right, they're examples of an exponential graph. So they're curved. If your common ratio is greater than 1, it's growth. If it's between 0 and 1, then it's decay. All right, and that's all written here. All right, and then we've got our recurrence relations. So again, same deal as with arithmetic. You just need to know what your starting value is, or your initial value means the same thing, and your common ratio. All right, and then here we've got our common ratio and our starting value. All right, we're not going to look at any financial applications, so don't worry too much about this part here, but just a quick recap. Geometric sequences, we've got compound interest, investments, and loans. So that's an example of geometric growth. And then geometric decay is reducing balance depreciation. All right, so that's just a quick recap. All right, let's have a look at doing some questions. All right, we're not going to do every question here because it's going to take forever if we did. But just to get an idea of, what arithmetic is and what geometric is. Oh my God, my phone won't stop ringing and I just keep sending it to voicemail because I do not answer phone calls if I don't know who it is. All right. Consider the following sequence. State the starting value of the sequence. Easy peasy, Japanesey. It is 5. All right, if we were to write that in a recurrence relation, all right, V0 is 5. All right, determine the rule for the sequence. Now, you do not want to get rule and recurrence relation mixed up. They're two separate things. So let's say, oh, I can't remember what that is. That's when you just have a look at your poster, guys, and we go here, here's your rule. All right, Vn equals V0 plus n times d. So you would have that open. All right, let's write that down and then we can substitute in the values. All right, so there is our rule. All right, sorry, I just had to, the phone won't stop ringing. Okay, so I just need to substitute in, remember, for the V0 and for, oops, not N, silly me. I need to just get rid of that. Can I get rid of that? Let's start again. All right, ND. It's only because I wouldn't usually put it in that order, but that's what the textbook has done, so let's be consistent. All right, so our rule, Vn equals, so V0, our initial value is 5, plus n times d, which is 6. So our common difference is 6. Now, there's nothing wrong with actually leaving it like that. I would probably clean it up and write 6n, but if you write n times 6, it's the same thing. No problems. It's all good. Now, if we were to continue using this rule, all right, let's write down the next 3 terms. So this is part C. So our initial term, which is V0, is 5. Now I'm going to use the rule for each one. V1. So if I was to use this rule, all right, my value of n is 1. So we have 5 times, oh, sorry, not times, Karen, come on. Let's get rid of that. Plus 5 times 6 times 1. Sorry, 5 plus 6. Oh, sorry, I should put my phone away because it keeps going off. All right, which is 11. All right, which we can see. All right, so V2, 5 plus 6 times 2 gives us 17. All right, we can see that. Now, if I wanted to do the next 3 terms, all right, so we're going to skip 23 and 29, otherwise we'll be here forever. So we've got, this is V0, V1, V2, V3, V4. So we want to work out V5 is the next one. So we do 5 plus 6 times 5, which is 35. If we want to do V6, 5 plus 6 times 6, which is 41. And you can see I'm just adding 6 each time. So, but if we had to do a very high number, so let's say we had to do 100, right? We can't keep doing that. So we go V100 equals our starting value plus a common difference times 100. So that would be 105. So the rule is really good if you need to go to a higher number, all right? Instead of going, so a recurrence relation, you would go 1 by 1, whereas a rule, it's very useful if you have to find a very high number, like that one there. All right, let's have a look at, I'm going to just skip a few. Yeah, so let's have a look at this question here. Let's have a quick sip of water. All right, so we've got to find the required term. So we're going to work out the rule first, and then I'm going to use the rule to find the required term. So let's have a look at question A. I'm just going to do 1. All right, so our initial value is 18. Actually, we'll do 2. We'll do 1 where we're going down as well, so decay. And our common difference, which is D, so I can see we're going up by 3 each time. So my rule is going to be Vn equals 18 plus 3n. All right, I've substituted in my initial value and my common difference. We have to find, oh, they're using T. I swear I didn't. All right, so here they've used a different letter, not V. So let's just get rid of these these and put in t. Should have taken note of that. All right, so T35 is equal to 18 plus 3 times 35. So you don't have to go through it 35 times to work it out, and then you can just do that on your calculator. All right, so just do 18 times 3 times 35. So 1890. Let's make sure that's right. No, did think there was something wrong there. There should be a plus. Oh, looks like that number just looks a bit too high for my liking. 123. So that's a good example of why you should always check your answer, because I was like, yeah, that looks a bit high. All right, so 123. An example of arithmetic decay. So let me just have a quick look. So G. Now, if you can't work out what the common difference is, remember you just take two values and then we just do the difference between the two of them. So we take the second one, subtract the previous. All right, so 68 minus 82. So 68 minus 82. Negative 14. So our common difference is minus 14. And we're going to use t again. So your initial value, t0, is 82, and your common difference is negative 14. So if we wanted to work out the general rule, it's Tn equals 82 minus 14n. And for this one, we're working out the 21st term. 82 minus 14 times 21. I need to just make my calculator up a bit. 82 minus 14 times 21. So negative 212. Now there is other ways you can do this on your calculator. So let's just use the first one as an example. So if you weren't going as high as 35, you can just keep pressing enter each time. So for this one, we're doing 18 plus 3. All right, and then I'm just going to, you got to wait till it comes up with ans for answer, plus 3. And then you can just keep pressing enter each time. So that's not a bad way of doing it if you weren't going as high. I wouldn't do it for 35 because imagine doing that 35 times and you might end up with the wrong value. So I don't tend to use that. Another thing you can do is using sequence on here. We can just clear what I already had in there. All right, so my sequence, I'll do the first one again. So 18 plus 3n, and we just find n up here. Our initial value we've got to put in, excuse me, oh, you let me go on. All right, and then we just go here and we get the values. All right, so why have we done, it hasn't done the first term properly. Oh my gosh. All right, I need to pause, figure it out. It didn't take me too long to work out because I should have there A0. Oh no. AN. I am so silly. I should stop making these videos because they do make me a bit tired. That is a recurrence relation I'm putting in, not a rule. And that's it's probably a good example of making sure that you know the difference between the two. I was wondering why it was asking for A0 and then it just clicked. They've got to input the recurrence relation, not the rule. All right, so it's just around the other way to how we're used to writing it. So writing your initial value and then the relationship between each terms, but then it's going to work for you. So when you're putting it into sequences on your calculator, you're putting in the recurrence relation, not the rule. So you can see there's the recurrence relation. Now you could just scroll down to 35. Oh no, was it 35? Yeah. And one more. All right, so there you can see 123. Oh, it's going to keep going because I press it too many times. Some of you might not see beyond 5 and you're like, oh my gosh, I can't see anything else. All right, so just to change that, oh, now I have to remember. So this one. All right, so starting value, end value. So you can start at 0 and at whatever you like. I just do 50 because why not? You don't want to do it too high because you don't want your calculator to be thinking a lot. So 50 is probably high enough. All right, so you can put both arithmetic sequences and geometric sequences in here. Oh, and there's the word recursive. All right, and I wonder if that's, oh, that's probably, I've never actually done it this way. Let's see. And there's in there, which I could have just pressed. Yeah, I'm going to do 2 ends. Maybe it works that way. Yeah, there we go. All right, so there's your recurrence if you want to do it recursively, or there it is if you want to use a rule. All right, there you go. Learn something new every day, guys. All right, then we get into recurrence relation. So let's just do one example of a recurrence relation. Let's do this one. All right, so remember with your recurrence relation, you've just got to substitute in your initial value and your common difference. Easy peasy. So for question A, your initial value is 7 and your common difference, we're going up by 4 each time. So remember with any recurrence relation, you must have the V0 part. All right, if you don't, it's wrong. And then we've got Vn plus 1 equals Vn. Remember that common for every recurrent arithmetic sequence recurrence relation. And then we've got that plus 4 on the end. So, oh, it was up the top there. Just notice as I pressed. All right, so we're just putting in that part. But I also just noticed before I went, here it is as well. So you could use T. It didn't say what letter to use. So if it doesn't say what letter to use, you can use T, you can use V. Do not use N. There's probably other letters you probably shouldn't use either, but just, yeah, T or V. And you can see in the next one we've used A. All right. Here we've got writing down the first 4 terms. All right, so with recurrence relations, usually in an exam it says show using recurrence relations, blah, blah, blah. So you must... So if we were doing, let's do B actually, because we haven't done K. All right, so now you don't have to write the first one because it's already written there. I just prefer to do so. V1 is equal to, now using your recurrence relation, we've got Vn, so the previous value, minus 5, and that is equal to 33. V2. Your previous value minus 5 is equal to 28. V3 is your previous, oops, that's not the previous value. And my son's just got home, 28 minus 5 equals 23. And for first, well, there's your first 4 terms. I might just do V4 just for funsies. 23 minus 5 equals 18. Now, if we were to graph them, here we've got our values of n. So we've got 0, 1, 2, 3, 4. And I might go up by 10. And I'm going to have to just pause for a sec because he's about to walk in the door. All right, so if your x-axis is n, so then your y-axis is Vn. All right, so that's your, it's kind of like your x and your y if you were doing a linear graph. All right, so our first value is 38. So at 0, we go up to 38, which is here. And then for V1 is 33. And then V2, 28. And remember, this is arithmetic, so it should be forming a straight line. V3 is 23. And V4 is 18. All right, you can see, clearly does a straight line. All right, so that's, you can see it's a linear graph. It's, don't have to put a line through it because it is, yeah, just the points on the line. All right, and then we've got applications. So we'll do the applications in a separate video. So let's just squiz through to some geometric. All right, so let's have a look at the difference between geometric and arithmetic. So To find the ratio, remember we just take the second value divided by the first. So for question A, second value is 8 divided by the first is 2. And you can see you're multiplying by 2 each time. But sometimes it's not that straightforward. So let's do B. So 3 divided by 1 is 3. C, 8 divided by 16. So this one is a half. All right, so you can see it's going down. Now it's not dividing by 2, it's multiplying by a half. So common ratio, we're always multiplying. And this one, 24 over 48, so that's also a half. So we're halving each time. All right, I'm going to skip that one. Let me just have a look. Consider a geometric sequence that starts with a value of 20, where each subsequent term increases by 10%. State what each term must be multiplied by to find the next term. So remember when you've got a percentage, so we'll just go to geometric, scroll up here. All right, so if it grows by a percentage, we just got to substitute it in. All right, if it decays by percentage, then it's just the second one. So for, oops, wrong one. This one here, we're going to go 1 plus 10 over 100. And we get 1.1. What that actually means is we take 100% of the value and we're going to add an extra 10%. So basically we're taking 110% and as a decimal it's 1.1. So the next three terms, so we start off with 20. All right, so actually let's write them down in terms of their term numbers. So initial term T0, T1 is 20 times 1.1, which is 22. And then T2 is 22 times 1.1. And I'm just going to do that on the calculator just in case I get it wrong. 22 times 1.1, 24.2. Whoops. Oh my gosh. 4.2 T3, 24.2 times 1.1, and you could just go on here times 1.1, and then you can keep pressing enter like we did before. So let's just end on this one, 26.62. Now you could also use the sequence function. So if we go to menu, go to sequence, it's a little bit slow. Come on guys. All right, and we can change what we had there. So we need to remember putting a recurrence relation. So our initial value was 20, and this one is a, oh my gosh, or a geometric. So if you need to, you can go back to geometric, have a look at your recurrence relation. So it's just R times Vn. So let's go back here. So our common ratio is 1.1 times, and we're just using different letters here, so AN. Oh, I thought I did that before. Okay, there we go. So 20, 22, 24.2, 26.62, and you could also use the rule there if you wanted to. So going back to here, looking at your rule, so R to the power of n times V0. So 1.1 is our common ratio times n. It's going to work for me. It's going to multiple n's now. Whoops, I forgot to put the 20 in. Oh, why isn't this working for me? Alright, I had to pause what I was doing because I just realized I did not have the right thing on. And what's happened here? Okay, let's just go back. All right, so I didn't put the rule down properly. Oh, I keep getting mixed up between my recurrence relation and my rule. So it's because I'm jumping back and forth between them. So if I had it open, you can see here, your R is 1.1, right? So there's your R there. So the power of n, which I didn't do before, I did times, and then times your initial value, and there's our answers there. All right. Let's move on. Writing a recurrence relation, it's pretty straightforward. All right, so let's just have a look at this one here. Maybe we'll look at D. All right, so we've been given the recurrence relation, so sometimes you need to interpret that. So our initial value is 10,000 and our common ratio is 0.5. So we want to find, what do we want to do? T30. These are two separate questions, by the way. This is a separate question. All right, so we can put that recurrence relation in here. So our starting value is 10,000. And we've got 0.5. All right, so remember that's an example of decay. So 0.5 times AN. I know it says T in there, but we can stick with AN. And then there we go. Now we want to do, what was that, T30. So let's scroll down. All right, and if I was to look at that, I've got 0.00000. So if I just press on it, you can see I get this number here. And you might still think, oh my gosh, that is still just a ridiculous number. What's this e to the negative 6? If you want, you can highlight it. And I'm going to copy it into the main screen. All right, and there it is. Now, you do need to have your calculator in the right settings for that though. So if you're not seeing this number, you're still seeing the E, you can go here, just go to basic format, and you want to have number 2 here. All right, and that should fix it. If not, that E just means times 10. So you could just write times 10 to the negative 6. It's an example of scientific notation, which you've definitely covered before, but probably forgotten. So that E just means times 10. So you can write that whole number, times 10 to the negative 6. However, I don't think you would have a question like this in an exam, but sometimes it will come up, especially maybe in methods, more so than general, but you don't want to freak out with that E. You can't write that down in your SAC or in your exam, but you can write times 10, which is the same thing. I would just copy and put it into the main screen, just so you've got that whole number there. All right, I'm just conscious of how long this video is. So then we've got application. All right, so let's just leave it there because we've got enough probably information on arithmetic and geometric sequences. And in the next video, we'll look at their financial applications, which is probably more important.